Welcome to the Deep Dive. Today, we're pulling back the curtain on some pretty amazing tech in aviation safety, specifically the emergency systems.
Right, the things you hope you never need.
Exactly. And we're focusing on one key component, the Ram Air Turbine, or RAT. It sounds, well, almost dramatic, doesn't it? Like the pilot's last handshake with survival.
It really is. And
Yeah.
you know, safety in aerospace, it isn't just about having backups like a spare tire. It's deeper than that.
Deeper how?
It's about genuine resilience. And that resilience, well, it really shows its value when everything else, absolutely everything, has failed. The RAT is a perfect physical example of that thinking.
Okay, resilience. I like that.
Yeah.
And to make this real, we're grounding our discussion today in a specific event. Air India Flight 171 back on June 12, 2025. It involved a Boeing 787 Dreamliner.
A significant event, yes.
So our mission here is to unpack what we know about the RA system, particularly on the 787, using AI-171 as a lens, and then look ahead a bit. See how maybe AI, artificial intelligence, could change the game for aviation engineering.
Sounds like a plan.
Great. So this RAT, let's break it down. What is it? Fundamentally, how does this thing actually work?
Okay, basically it's a small turbine, think of a little propeller almost, and it's powered by the wind, the airflow rushing past the aircraft. That's why it's called Ram Air.
So it's like a mini windmill.
Sort of, yeah. A mini generator. Its whole job is to pop out and start spinning when the plane loses its main hydraulic or electrical power. A catastrophic failure scenario, basically.
And on the Boeing 787, you mentioned it's maybe a bit different.
It is, because the 787 is what we call a more electric aircraft. It relies much more heavily on electrical systems than older designs. So the RAT isn't just, a nice-to-have backup. It's absolutely core, a final line of defense built into its architecture.
Right, that makes sense. The more you depend on electricity, the more critical that emergency electrical source becomes.
Precisely. On the B787, the RAT directly powers crucial electrical buses, both the 115 VAC and the 28 VDC systems. It also supports something called the Remote Power Distribution System, the RPDS.
RPDS, what's that?
Think of it as the Emergency Electrical Control Center. It smartly sends the limited power from the RAT to only the most essential things.
Which are?
Primary flight control, so the pilots can actually fly the plane, basic navigation displays, essential communication radios, and importantly, it also provides a small amount of hydraulic pressure.
Hydraulics too, even though it's mainly electrical.
Yes, just a minimal amount, but enough for basic flight control surface movement. So yeah, this isn't just a propeller spinning for looks. When everything goes dark, this little turbine is the absolute core of keeping that aircraft controllable. Survival, really.
Okay, that's
Yeah.
a lot riding on a small turbine. You mentioned minimal hydraulic pressure, though. Yeah. Is that really enough if things get rough?
It's minimal, as in truly minimal. Enough for basic commands, keep the wings level, make gentle turns, manage descent. Not for, aggressive maneuvering. It's about maintaining control, getting stable.
Got it. And when does it actually deploy? Does the pilot have to push a button or?
Yes. Primarily, it's automatic on the 787. The aircraft detects severe conditions and deploys it itself.
What kind of conditions?
Things like both engines failing, or losing all main electrical power sources, the main buses, a complete hydraulic system failure, even certain overheat or fire situations, or if all the electric pumps that normally power the hydraulics fail.
So pretty dire situations.
Absolutely. The system is designed to react instantly when things go very wrong. Now, there is a manual switch in the cockpit, but that's mostly used for ground tests or maybe in some really unusual edge case scenario the computers didn't anticipate.
And what happens in that split second between losing power and the RAT spinning up? Is the cockpit just dark?
No, there's a bridge. The main aircraft batteries kick in immediately. They power the essential flight deck instruments and systems for a brief period, just long enough for the RAT to deploy and start generating its own power, so the crew isn't left completely in the dark.
Okay, that critical transition is covered. Makes sense. So the theory is clear, but let's talk about the real world. Air India 171. What actually happened there? Remind us of the basics.
Right, June 12th, 2025. A Boeing 787 Ahmedabad to London.
And what were the first signs? What did people on board or analyses show?
Well, initial reports, eyewitness accounts, things like passenger videos, even some audio analysis point to classic signs of a power issue. Flickering cabin lights, then apparently a loud bang. Could be engine trouble, could be something else shifting power.
And the key observation?
The key thing confirmed pretty quickly was the RA deploying while the plane was still in the air. You could apparently hear its distinct high-pitched whine. That sound is a clear signal. major system failure underway.
And pilots.
They initiated an emergency descent, standard procedure. The flight data recorder and cockpit voice recorder, the black boxes were recovered, of course, but the full analysis, as far as we know, is still ongoing. Takes time.
Right. But here's where it gets technically interesting and maybe a bit worrying. You mentioned RATs have limitations.
They do. And it's a fascinating point. They aren't equally effective at all altitudes.
How so?
Because they need airflow. Ram Air. Sufficient air density and speed to spin the turbine fast enough to generate the required power. At very high altitudes, the air is thin. At very low altitudes and lower speeds, especially during approach, there might not be enough airflow, enough energy to power everything it's designed to support. There's a sort of optimal range.
Okay, so not always peak performance. And how does this connect back to the Air India flight?
Well, the report suggests that when the RAT deployed on AI-171, the aircraft was already at a, let's say, lower than optimal altitude for the RAT's peak efficiency.
So what does that mean practically?
It likely means the power output from the RAT was reduced, less juice available, and that in turn probably meant the pilots had potentially quite limited access to some navigation systems or maybe reduced responsiveness from flight controls. They had some control, clearly, but perhaps not the full suite expected from the emergency system.
That sounds concerning.
It is. It raises a fundamental question, doesn't it? We engineer these systems, we test them, often under fairly ideal conditions. But emergencies, they almost never happen under ideal conditions. This AI-171 situation, it's a bit of a red flag. It highlights that potential gap between design assumptions and messy reality.
Yeah, it really makes you think, are we just designing systems to react after the disaster strikes? Is there a way to be smarter to get ahead of it?
That's the million-dollar question.
The sources we reviewed brought this up directly.
Yeah.
Like, are these emergency systems truly future-proof? Could something like AI, predictive analytics, maybe warn us before total failure? Could it even prevent the need for the RT in the first place sometime?
Exactly. Or could an intelligent RT maybe behave differently?
How do you mean?
Could it perhaps adapt its deployment, maybe wait slightly if the altitude isn't good, or deploy differently based on why the power was lost or the current airspeed?
That's a really interesting idea. So AI's role here is...
It's potentially huge. This is where we absolutely need to be looking. Imagine AI models constantly analyzing sensor data, looking for tiny anomalies, patterns that predict a failure before it becomes catastrophic.
Predictive maintenance on steroids, basically.
Sort of, but integrated right into the flight systems in real time. These AI models, fed with live telemetry, could give the flight computers a heads up. Enough warning to perhaps reconfigure systems, or yes, even preemptively deploy emergency systems like the RAT before the actual failure threshold is hit. It's moving from being reactive to being proactive.
Give me an example. What might that look like?
Okay, imagine sensors detect subtle vibration changes or temperature fluctuations in an engine, patterns that AI has learned often precede a failure. The system might not wait for the engine to completely flame out. It might say, pre-spool the RAT, getting it ready.
So it's already spinning when needed.
Potentially. Or think about fuel. AI could continuously analyze fuel quality sensors using machine learning, flagging potential contamination issues way before they cause engine problems. Or maybe, if predictive thresholds suggest a major electrical failure is imminent, the system starts bringing alternate power sources online before the main ones die, not just after.
Oh, that feels like a genuine leap forward.
It really is. And look, this isn't science fiction anymore. The capability is developing. It's a design frontier we absolutely have to explore for the next generation of aircraft safety.
It shifts the whole philosophy, doesn't it?
It does. You have to accept that failures in complex systems are somewhat inevitable over the long run. Things happen. But every single incident, every failure, it's not just a tragedy or a problem, it's data. It's an invitation to innovate.
Learn and adapt.
Exactly. Use these case studies, like AI-171, not just to find out what went wrong, but to fundamentally transform how we design the next system. How could an intelligent RF, for example, have adapted its power output knowing the altitude was low? Or maybe even briefly delay deployment if a rapid descent was needed first? These are the blueprint questions.
Which brings us back to that idea you mentioned earlier. Redundancy isn't the same as resilience.
No, it's not. AI-171 really underscores that. Having a backup, the RAT, is redundancy. But if that backup has limitations in the real-world chaos of an emergency, like the altitude issue, then you haven't achieved full resilience.
So resilience is?
Resilience is about anticipating failure. anticipating the non-ideal scenarios, the messy realities, and designing systems that can still function effectively, perhaps adaptively, even then. It means thinking of systems like the RAT not as bolt-on afterthoughts, but as integral parts of an intelligent, adaptive aviation architecture.
Yeah. The goal shouldn't just be more black boxes to tell us why things failed.
We need more blueprints for survival. Blueprints designed with foresight, anticipating the unexpected.
Well, that's quite a journey we've taken, from understanding this critical piece of hardware, the RAT, seeing how it performed in a real-world stress test with AI-171, and now looking at how AI could really change the future of keeping planes safe.
It's a fascinating intersection of engineering, data, and forward thinking.
So a final thought for you, our listener, to maybe mull over. Think about this idea of resilience versus just redundancy, and this concept of anticipatory design, designing for potential failures before they happen.
Yeah, how could those ideas apply elsewhere? Not just aircraft, maybe complex systems in your own work or even challenges in your life. What potential failures can you anticipate and maybe design a more resilient approach around?
That's a really powerful question, something to definitely chew on. We hope you'll continue your own deep dives into topics that grab your interest. Thanks so much for listening.